And welcome to SanfordFlipMath. We are doing a little pre-calculus stuff here. We are in the Demana Waits Foley Kennedy Pre-Calculus Functions and Graphs book, 4th edition, and we are working with basically doing different things with functions. Last section was all about, or the last video was all about doing composition and arithmetic with functions. This one's going to be focusing specifically on inverse functions mainly, and a little bit with parametric, and working back and forth between the two forms. Depending on time, parametric might get short. We'll see. Inverse functions. We have a basic idea of what inverse means. Like if we were talking about x plus 3, the inverse, most of us are pretty comfortable with the idea of minus 3 because, you know, the inverse operations of addition, the inverse operation for addition is subtraction, the inverse operation for subtraction is addition, and similarly the inverse operation for multiplication would be division. And that's all pretty good if you're only talking about one operation at a time, but it's not real tight. And so what inverse really is about when you're talking about functions is this, and so this is just notation. So this means the inverse of f. And the big issue here is this is not the same thing, and you aren't going to like this, as this. Okay, so f inverse is not the same thing as the multiplicative inverse, see I'm fancy, of f of x. This means reciprocal. This would mean 1 over f of x. And this does not mean that, and I wasn't the one who made up this notation, and I'm sorry it's like this, but when you jam that -1 in between, it means inverse of f of x, okay? So inverse, the conceptual idea is it's a rule, it's a function, it's an equation that undoes whatever f of x does. So for instance, if I have f of x equals, let's say 2x plus 1, if I do f of 1, well 2 times 1 is 2 plus 1 is 3. Okay. Well, if I want to get back from that 3 back to the 1, I need to undo whatever happened. Excuse me. So the idea is f inverse of 3 ought to get me back to 1. The question then is, what's the thing in the middle that'll do that? Okay, so before we do that, and you guys will be, you know, you can feel free to pause and figure that out. So notice this was the original x, and this is the original y for some function. So a was a y, I'm sorry, a was an x value. Okay, so this was x, and this was y. So the idea is that what used to be the y values inside this were from originally the y values of the original function. Here's the short version. X and y switch. That is the heart of the issue. Okay, so let's take that bad boy for a spin. Let's take this thing that you guys maybe already paused and figured out what the inverse was. This says y equals 2x plus 1. To do inverse, what we're going to do is switch x and y. So x is going to come over here, y is going to come over here, and this is 2y plus 1. And now, if we want to actually get the function that undoes the other one, we're going to solve for y. So subtract 1 from both sides and divide by 2. Now, how you leave this, you have some options here, okay? So this currently says y equals x minus 1, the whole thing over 2. Now, if you'd like to divide each of these separately, kind of distributing the 1/2, this would be like 1/2 x minus 1/2. It's entirely up to you how you want to leave that. You know, I'm fine with this. I'm fine with this. Okay. Also worth noting, this is f inverse of x. Now, if that's true, what I said back here was, if we do, I'm just going to use the x minus 1 over 2 version of this to see if it actually works. Put 3 in here. Well, 3 minus 1 is 2. 2 over 2 is, hey, look at it, worked. Woohoo, Happy New Year. Okay, let's do another one. Okay, all right, so let's say we have f of x, and again, there's nothing sacred about f. Let's say we have f of x equals, let's do x cubed plus 1. Okay, if that's true, and if I want to know what the inverse is, okay, so here's my goal, is to find f inverse. Now sometimes they'll leave it like that and they'll just say f inverse. Sometimes they'll say f inverse of x. So just understand that they're the same thing. Okay, there's some flexibility in this notation. Okay, so what I'm going to do, I'm going to treat this like y equals x cubed plus 1. Okay, because just I think it's easier to keep track of y's, and I know you're more comfortable with y's. Okay, so to do the inverse, we're going to switch x and y. Yeah, that's a nice y. Okay, so this becomes y cubed plus 1, and this becomes x equals. Now it's just a matter of solving. Okay, so I'm going to subtract 1 from both sides. And then I want to undo the cube, so I'm going to do a cube root. Well, that was nice. So the cube root of y cubed is y. I'm going to flip this around because I just like this form better. Okay, so again, this is f inverse of x, or just straight up f inverse. Okay. So supposedly, if I wanted to undo y values from this and get back to x values, then I would use this. And if you think about it conceptually, that really ought to make sense in terms of, you know, if I cube something and then add 1, then wouldn't it make sense if I want to undo that, I would undo the 1 and then uncube it. Okay, it's kind of like putting on socks and shoes. If I you know, when I put them on, I have to put socks on first, and when I put on the shoe, oh, hello, didn't mean to do that. Hey, that's my boy. You know, I have my foot here with toes. I know you're shocked to find that out. I put on my socks, and then I got to put shoes on over that. These are my brand new pair of Mikeys. Yeah, okay, I'm making that up. Okay. Well, the problem is if I want to get back to my foot, I have to undo that stuff in the reverse order. So I undo the shoe first, undo the sock, and then I'm back to the foot. Well, this plus 1 is the shoe. This cubed was the sock. So undo the shoe first, then undo the sock. Okay, I know that was kind of a Algebra 1 little analogy there, but it works. Okay? All right. What I'd like to do right now is I want to just look at something that I think is kind of cool, and it's not just cool because I think it's cool, but you actually need to understand how this works. Okay? Let me pop back and write down those equations again. So this is x cubed plus 1. Okay, so f of x equals x cubed plus 1. And then the other one was, I believe, cube root of x minus 1. Yeah, that's it. Okay. Okay, so f inverse, the y values for it, cube root of x minus 1. Okay, look at this. I'm going to do some graphing. Okay, so let's graph x cubed plus 1. Now, I happen to know that the x cubed graph looks like this. I also know that it normally crosses at 0, 0, and this went up 1. So I'm going to start at 0, 1, okay, and that does work in this equation. When I put in 1, 1 cubed is 1, plus 1 is 2. Now 2 cubed, 8, plus 1 is 9, so that's going to be way up here. And similarly, okay, all right, let me pop back up for a second. When I put in negative 2 times negative 2 times negative 2 is negative 8, plus 1 is negative 7. Okay, so negative 7 be right here. Okay, and here we go. Okay, let me scroll back up so I can finish that. Ooh, a little bit tight there, or not tight enough, sorry. Yeah, that'll work. Okay, this is going to cross 0 at x equals 1. And it kind of looks like a square root graph. The biggest difference is that it has a negative too, because you can actually take the square root of negatives. Okay, so like for instance, if I put in 2, 2 minus 1 is 1, cube root of 1 is 1. If I put in 0, 0 minus 1 is negative 1, the cube root of negative 1 is negative 1. Okay, if I put in, now I'm going to put in a big number because I want this to work a certain way. I know that the cube root of 8 is 2, so if I put in 9, I get 2. Okay, so 9, 2. A little bit far, it shouldn't cross the 2 until it gets to the 9, and it'll be close enough. And same idea here, if I do negative 7, negative 7 minus 1 is negative 8, cube root of that is negative 2. Okay, so negative 7, negative 2. Okay, now what I need you to see is look at these graphs. There's something kind of special about these graphs. And what's special about these graphs is that they are the same shape. So when graphs are inverses of each other, graphs are the same shape. Not only are they the same shape, but they are a direct transformation from one to the other. And the question that I have is, what is that transformation? Now, I can't really, sit here and wait for you to answer it, that question, but here's a big hint. So they are reflection images over a very specific line called y equals x. Now, that line is not all that mysterious. It's just y equals 1x plus 0. It is the line that have all of the x values and the y values the same. For instance, right here, the ordered pair, oh, what is that? That's not even, I was thinking it was negative 1, but it's really not. It's negative 1, negative something, is shared on both graphs. Now, look at this point right here. This is at 2, 1, and this point right here is at 1, 2. This point is at 1, 0, and this one, and this point is at 0, 1. Okay, so my question to you is that surprising? That 1, 0 is on the inverse and 0, 1 is on the original. Okay, I just want to pop back here for just a second. How did we start this crazy journey? We switched x and y. So pop back over to the graph. Oh my goodness, look at that. We switched x and y. We switch x and y. Okay, so a couple things that need to happen here. The effect on going from one graph to its inverse, you can actually do that by just switching x and y's. You don't really even have to find the inverse if your goal is only to graph the inverse. Okay? What you do need to understand also is that an inverse and an original, the inverse equation and its inverse, the inverse equation and the original equation and its inverse, are reflection images across the line y equals x. That sounds like a really good question for a test. Just saying. Okay. Okay. Now, I want to do one more that's kind of like that. Okay. So what I'd like to do is, let me throw another grid on here. Okay, cool. And I want to start with y equals square root of x, just plain old square root of x. Okay, so here's 0, 0, 1, 1, 4, 2. Now, before we get all excited about this, I want to remind you what the domain and the range are for this particular equation. Okay, the domain is only the x values to the right of 0 and including 0. And the range is, this is a really bad example because it's not going to be nearly as exciting as I thought it was going to be. All right, so I'm changing it on the fly. Sorry about that. I know some of you are diligently taking notes, and I appreciate that, and I'm going to make a very slight change to this particular equation, and it's going to be the square root of x plus 1. Now, please note that this plus 1 is on the end. So you tell me, we know what that parent function looks like because I just had it up here. If I put a plus 1 on the end, on the outside, it's on the outside, it's about y. Do what it says. It's addition or subtraction, so it means it's a translation. This whole thing should shift up 1. So here comes the graph, the new graph. All right, so the domain is all of the x's greater than or equal to 0 still, and the y values are greater than or equal to 1. Okay, that's called real life, folks. Sorry about that. Okay, now what I want to do is the inverse. Now, if this is if this was f of x, then the inverse would be x equals the square root of y plus 1. Now, if I'm going to solve that for y, I need to subtract 1, and I need to then square both sides. I'm going to change colors so that it's a little more obvious what I'm doing. So this is now y equals x minus 1 squared. Okay, now it doesn't really need to be squared out. In fact, it's easier to see what's going on if you don't. So here's y equals x squared would be the parent function. We know what that is. And it shifts to inside inverse, so it shifts right 1. Okay, so here is this graph, and again, looking something like this. Okay, and well, there's another side to this. Okay, now here's my question for you. Is that really the inverse of this function? Or is that the inverse and then some? Okay, now let's think about what happened with domain and range. Okay, here's domain and range of the original. Domain is all about x, range is all about y. If I'm going to the inverse, shouldn't domain and range just trade? Shouldn't x and y trade? So here's the issue. The domain and range of the new function, the inverse, there it is, should just be the same thing, only switched. Well, this was greater than or equal to 1 then, and now that we made them x's because we traded x and y, and then the y should be greater than or equal to 0. Well, what that means then is that we have a little bit too much graph here. So goodbye to you, and I know I got some stuff to fix. I don't know if you can hear it, but the wonderful Southfield High School marching band is outside, you guessed it, marching. I don't know if you can hear the thump, thump, thump of the drums, but there it is. All right, so when you do inverse, x and y switch. Okay, so inverse. Switch x and y, solve for y. When you do inverse on the graph, it reflects over the line y equals x. When you do inverse, because x and y switch, domain and range switch. Inverse. That was exciting. Okay, I'm going to spend just a few minutes, hopefully less than 5 minutes, talking about parametric equations, parametric functions. Parametric equations, parametric functions have a weird thing in the middle of it, and basically it is a parameter. Oh, look at that. Never mind. We will just finish up with proving inverses. Okay, so I forgot one little detail and we have to deal with it. Okay, so sorry about that. Psych. We'll talk about parametric at some point. It just won't be right now. Okay. If I wanted to prove two functions are inverses, okay, so I have all this evidence, like, looks like if I solve, switch x and y and solve, I get a different equation. If I look at the graph, there's a reflection across y equals x, but that's not really proof, that's good evidence. And you've heard this before when we talked about odd, even, or neither in terms of symmetry of graphs. And we did some crazy f of x, f of negative x equals something, depending on whether it was odd or even. Well, this is true also for proving that two things are inverses. Okay, so basically to prove that two things are inverses, g of x would be like the function that did something, and f would be the function that undid it, and you'd be back to x. And in the same way, f of x would be doing something, and g of x would undo it and get you back to x. That's conceptually what needs to happen, and in a practical way, what we have to do is show that that happens by doing composition of functions. So, for instance, let's say we have f of x is 3x plus 1. And let's say I have some other cool function and cleverly named g of x, and let's say I happen to think that 1/3 x minus 1/3 was its inverse. Okay, I want to prove that they're inverses. Okay, well, if there are in fact inverses, when I do f of g of x, I'm supposed to get x. And when I do g of f of x, I'm supposed to get x. So let's see if that really happens. So let's do f of g. F of g would be f of 1/3 x minus 1/3. So that means I'm going to do 3 times something plus 1. This sounds familiar from yesterday. So that 3 times, this is going to be 3 times, oh, I don't, hang on, back up. Not ready for that yet. Okay, so let's take this thing and put her there. Okay, so when I distribute this 3 times 1/3 is 1, times x is x. 3 times 1/3 is 1, again, so this is going to be minus 1. Okay, and that's from the 3 plus 1. Well, x minus 1 plus 1 is x. I am halfway there to proving that they are inverses. Okay, so this equals x. Sweet. Okay. Please note that this says and. I have to do them both. This is not done, we're not done proving that they're inverses. Okay, and I'll show you an example, maybe, that shows why this is necessary. Okay, so G says do 1/3 of whatever x is. In this case, it's f of x minus 1/3. Well, f of x, sorry, skipping a step, is 3x plus 1. Okay, so distributing 1/3 times 3 is 1, so this is just going to be x. And then 1/3 times 1 is 1/3 minus 1/3. Aha! X. Okay, so are f and g inverses? Yes, inverses. Yes, they are. And we proved it. This is the proof. This is what that would look like. Okay, so again, you have to do both sides. Okay, now if you have to go, just go. I'm going to go ahead and do one more example exactly like this, only completely different. G of x equals square root of x. F of x equals x squared. Are they inverses? Well, let's take it for a spin. The rule says that if I do g of f of x and get x, and I do f of g of x and get x, then they're inverses. Okay, so here we go. The square root of x squared. Well, f of x is the x squared. Okay, you're not going to like this. The square root of x squared would be x. if x was positive or if x was 0. But it's actually the absolute value of x. Yeah, I'm going to blow that right over that. Okay, and f of g of x, f of x would be something squared. And that something, in this case, is the square root of x. Well, the square root of x times the square root of x, assuming x is real, is, so this is just going to be x. So this side worked. This is not just x. And so I know that some of you are saying, but wait a minute, Mr. Sanford, isn't that the same thing? Tell you what, graph the square root of x squared. Just type into your calculator the square root of x squared, and I'm going to bet you money that your graph looks like this. And this graph is going to look like this. So the question is, are those the same thing? Okay, graph away. I'm going to do one other connection with this, and maybe this will help seal the deal. The domain of square root of x is x greater than or equal to 0. The range is y greater than or equal to 0. The domain of x squared, okay, that was domain and range. The domain of x squared, all real numbers, the range y greater than or equal to 0. Think about the graphs of those two functions. Okay, so this is the square root graph. Here's the x squared graph. Are those reflection images across y equals x? Sorry, they're not. The red one's only half a parabola. The green one is a complete parabola. Okay, I've gone way, way, way long, and I appreciate your attention. Thank you very much. See you in class.